This video, we're going to talk about how to use virtual work method to calculate the displacement or deflection in truss. So here we have a steel truss and we have two external nodes, FC and FB. So we need to determine the vertical displacement of joint C. So joint C is shown here, so the vertical displacement is delta C. Okay, so we have the external force at point B, FB equal to 100 kilonewton and FC equal to 200 kilonewton. So first of all, we need to calculate a reaction force. So we have one reaction force at joint at support A, because this is the roller support, and at support D we have two reaction force. So if we say this is first reaction force RDX, and this is second reaction force in y direction, so RDY. So we just randomly put the direction like this. So we can using the equation of equilibrium to calculate the three unknown reaction force. So look at these three unknown reaction force. First of all, we can easily come out RDY, because in y direction we have the force come together equal to 0. So we have RDY negative minus FB equal to 0. Okay, so because RDY is go up, our FB is going down, so we can write down like this. So we have RDY equal to FB equal to 100 kilonewton. So RDY is 100 kilonewton. So once we got RDY, then let's look at RDX. So to come out RDX, we can using the moment equation of equilibrium at joint A. Okay, so we can write down moment equation of equilibrium at joint A. If we see the positive direction is going to clockwise, so let's see how many moments we have from the force to the joint A. First of all, we have RDX. So RDX have a moment is go to the clockwise, so it's positive. So we have RDX times the lever arm is 4 meter times 4. This is first moment. Second, RDY is go through the joint A. So RDY have a 0 moment. So then is FC. FC is go to clockwise as well, and so it's positive FC times the lever arm is 4 meter as well. And then the last one is FB. So FB is go to clockwise, so it's FB positive times the lever arm is 3 meter equal to 0. So we plug in the value of FB and FC. So we have RDX times 4 plus FC is 200 kilonewton times 4 plus FB is 100 kilonewton times 3 equal to 0. So from this equation we can derive RDX is negative values is 275 kilonewton. Okay, so we just easily calculate RDX. So RDX is negative. That is mean our initial assumption of the direction go to right direction is not correct. So then the correct direction for RDX is go to left hand side direction. So RDX is 275 kilonewton. Okay, so once we have RDX, we can write down the last equation of equilibrium in horizontal direction, that is in x direction equal to 0. We have RDX and we have RA. So if we see the positive direction is go to left direction, so RDX is positive, RA is go to red, so it's negative, and FC is negative as well. So we have FC equal to 0. So RDX is 275 kilonewton because we assume now the directions go to left, so it's 275. We don't need to use the negative over here. So it's 275 minus RA minus RFC is 200 kilonewton equal to 0. Then we got RA equal to 75 kilonewton. Okay, so RA equal to 75 kilonewton. So we got all reaction force RDY, RDX, and RA. So now we need to determine the member force. So to determine the member force, we start from the joint B. So look at the joint B. We have FB 100 kilonewton, and we can easily come out the member force in BC is 100 kilonewton as well, because if we draw the free body diagram on the joint B, we can easily find out the FBC is equal to FB equal to 100 kilonewton. And look at FBA, so look at this force. There's no other force in horizontal, we just have FBA, so that is mean this is a 0, so AB is 0 force members. So we got a 2 member force AB and BC. So now I would like to look at joint D. So look at joint D. If we draw the free body diagram for joint D, so this is joint D, and we have RDY is 100 kilonewton. We have RDX is 275 kilonewton, and we need to know the FDC and FDA. So we assume FDC and FDA is a tensile force. So for tensile force, the force is go outward from the joint. So we draw like this: FDC, FDA. So based on these free body diagrams, we can easily write down 2 equations of equilibrium in x direction or horizontal direction, or in y direction in vertical direction. So then we can know FDC is equal to 275 kilonewton and FDA is equal to 100 kilonewton. So we have member force for DC is 275 kilonewton, and for member DA we have 100 kilonewton. So we got AD, we got DC, AB, BC. So now the remaining member force is for AC. We can either look at joint C or look at joint A. So now I would like to look at joint A to come out of the member force in AC. So if we draw the free body diagram of joint A, so now this is joint A, this is joint D, so this is joint A, then we have on joint A, we have a force RA equal to 75 kilonewton, and we have member force FDA is 100 kilonewton. So member force for FDA is, we have calculated 100 kilonewton. And we have member force AB is 0, so we don't draw here. So we have member AC need to be determined. So we assume the member force FAC is go to outward from the joint. So we assume it's a positive force or tensile force. So before we move on to calculate the FAC, first of all, we need to calculate the angle over here. So how to calculate the angle over here. So this is theta. So in this right triangle ADC, so we know AD equal to 4 meter, DC equal to 3 meter. So we can easily calculate the AC will be equal to 5 meter. So then we can calculate the sine theta is equal to 3 over 5, and the cosine theta is equal to 4 over 5. So once we know sine theta and cosine theta, so then we can do analysis on the joint A. So at joint A, if we write down the equation of equilibrium in vertical direction, so at joint A, we have Fy equal to 0 in the vertical direction. We assume go up is positive, so we have first of all we have 100 kilonewton is positive, and then we have FAC have a component. So this is FAC have a component. This component is FAC times cosine theta. Okay, it's go up, so plus equal to 0. So from this we can come out FAC equal to negative 100 over cosine theta. So we can come out FAC equal to negative 125 kilonewton. Okay, now that means the initial assumption FAC is tensile force is not correct. That FAC is a compressive force. So we put FAC over here. So it's negative 125 kilonewton. So we have all the member force of this truss. So for the virtual work method, we call this is a real systems, and we need to build up the virtual systems to calculate the displacement, because we need to calculate the vertical displacement of joint C. Okay, so the virtual systems showing here. So we have we assume there's a unit node 1 applied at joint C go in vertical direction. So this direction is going downwards. You can put upwards vertical force as well, but here we just put the unit nodes going downwards. So 1. So once we have this force, so we need to come out the reaction force for these virtual systems and also member force for these virtual truss systems. So we assume the reaction force at joint point D is Rdx, Rdy, and for the joint A we have Rax. Okay, so we can easily find out that so Rdy equal to 1, because in vertical direction we only have two force, Rdy and 1. So Rdy, they are in opposite direction, so Rdy equal to 1. So this is Rdy equal to 1. And now let's look at the Rdx and Rax. So we can write down the equation of equilibrium at joint A equal to 0. So if we assume the positive direction is go clockwise, so at joint A, so Rdx have a moment in counterclockwise direction. So we have Rdx times the lever arm AD is 4 meter. So Rdy have 0 moment at joint A, and 1 unit node have at joint C have a bending moment is go clockwise, so it's positive 1 times the lever arm 3 equal to 0. So Rdx is equal to 0.75. So it's equal to 0.75. Once we got Rdx, we can easily come out Rax is equal to 0.75 as well. So we got reaction force, then we need to calculate the member force for the virtual systems. So we can easily know that. So the joint B is two-member joint. There's no external load on joint B. For this two-member joint, the member force for AB is 0 and the member force for BC is 0. So then let's look at the joint D. So the joint D, similar procedure at the joint D. If we draw the free body diagram, we have 1, we have 0.75, so the force at AD is 1, the force in the CD is 0.75. So here is 1, here is 0.75. Okay, so then let's look at the only one member we don't know the force is member AC. So look at the member AC. So if we look at the joint C, we can easily come out the member force in AC. So for joint C, if we draw the member force, so first of all is the unit, note A, and the member force in DC is 0.75, and we assume member AC is in tension, so this is member force AC, so this is FAC. Okay, this is FAC. So from the, if we say this angle is beta, so this angle is beta, we can easily know the sine beta is equal to, so this is 4 meter, this 3 meter, this 5 meter. So sine beta is equal to 4 over 5, and the cosine beta is 3 over 5. So then if we write down the equation of equilibrium for the joint C in x direction, so we have a component in x direction. FAC is FAC times the cosine beta, so plus 0.75, so this is 0.75 equal to 0, and we can easily come out FAC is equal to negative 1.25. So then we got the member force negative 1.25. Okay, so now we have all the member force for these virtual systems. So this is virtual systems shown here, and this is a real system shown here. So we got all the member force. Then the next step is using the equation to come out the displacement at joint C. So I will talk about it in the part 2, in the video of part 2. So see you later.